Hello, everyone. Today we're going to be starting our conversation on that much dreaded topic, phase diagrams. So, phase diagrams are essentially a convenient and succinct way to talk about the relationship of multiple systems that might be present in a mixture at a given time, whether they're solids, liquids, and gases. So, today we're going to be talking about coexistence that we've discussed several times before this, liquids and gases. So previously, we've been mostly focusing in on the structure of the liquid phase and more or less using the vapor phase as a metric to tell us what's happening in the liquid. However, we also can learn a lot about what's happening in the vapor above the liquid, and oftentimes this is going to be the more phase of more interest because it's generally more reactive. So, as is frequently the case, we're going to start with a fairly severe approximation. We're going to assume that the system is an ideal mixture. In other words, that it follows Raoult's law. And in this case, I can figure out the vapor pressure of, say, component A by simply knowing its composition in the liquid and the pressure and the vapor pressure if it acted as a pure system. Now, one of the important things to remember is that we're also going to have a certain amount of pressure generated by B, which can be then determined the same way. Well, and both of these together will generate a total pressure that's going to be net higher than either pressure independently, which again should make a lot of sense according to Dalton's law. However, what we can do is take all of these bits together to tell us a lot about what the composition of the mixture of the vapor is going to look like. So not so much what the mixture of the liquid is, but what is the actual vapor phase going to look like. And I can actually determine the mole fraction for the vapor phase, which we're going to give the symbol Y to help separate it from the symbol X to represent the liquid. So from here on out, X is going to give you the mole fraction of the liquid, and Y is going to give us the mole fraction of the vapor. And not too surprisingly, the mole fraction of the vapor is literally going to be the partial pressure of A over the total pressure. Well, we just generated an expression to give us the partial pressure with respect to A, which again is just going to be given by the mole fraction of A and the pure vapor pressure. And then we can divide that by the total pressure, which is going to be the essential partial pressure of A and the same expression for the partial pressure of B. And thus, if I know the mole fraction of A, I can use that to determine the mole fraction of B, and then look up the vapor pressures of the pure systems. Ta-da! We know what the composition of the vapor is by knowing the composition of the liquid. And this is actually a very powerful expression. But again, we can do this more explicitly by substituting in the mole fraction of A for the mole fraction of B being 1 minus XA. And again, this lets us combine the elements in the denominator. So now we can essentially figure out the mole fraction of A in the vapor simply by knowing the mole fraction of A in the solution phase, and again, by knowing the vapor pressure of the pure components, which can be garnered from the pure phase thermodynamic data, such as free energies of vaporization, as we've previously discussed. However, sometimes what will end up happening is we'll measure the composition of the vapor with some analytical instrument such as a GC, and what we're really going to want to know is what that tells us about the liquid mixture. And with a little bit of kind of messy algebra, we can go ahead and rearrange this expression. So we can get the mole fraction of A in solution based purely on the mole fraction of A in the vapor phase. So there's going to be a tight relationship in between the composition of the liquid and the vapor, and it's essentially going to be modulated by the vapor pressures of the pure A and B phases. And again, all of this assuming an ideal mixture. And again, we can use this information to go ahead and give us an expression for the total vapor pressure, starting from the simple idea that the vapor pressure of A can be given, again, according to Raoult's law, and the same thing with B. We can then go ahead and substitute in our expressions for XA and XB, both solely in terms of the mole fraction of A. Now, there's a bit of long algebra to this, but it's not too bad, rather just a little tedious. But at the end of it, what we end up is with quite a powerful expression, where we get the total vapor pressure for any mixture based solely on the vapor pressures, again, of the pure A and B species, and the composition of the mixture in the gas phase, which again, we can also still get by knowing, still obtain simply by knowing the vapor pressure of the composition of the solution phase. So this is actually a really powerful expression, because what all of these equations together tells us is that as long as I know one of these variables, I can get the pressure of each component, the total pressure, and the composition of all other components, both liquid and gas phase, as long as the system is at equilibrium. And one of the other things that you may notice is that all of these expressions also exhibit some relationship in between the vapor pressures of A and B. And this is going to have a lot of consequences on the composition of the mixture. So let's go ahead and take our two expressions. So for the composition of the vapor and for the total pressure, simply in virtue of changing the mole fraction of A in our liquid. So if I have a system where my ratio of the partial pressures of A and B, so this is going to be the vapor pressures of the pure systems, are equal, which is another way of saying that A and B are equally as volatile. They're equally as likely to evaporate. Well, in this case, as I increase the mole fraction of A in the liquid, what I find is the mole fraction of A in the vapor essentially has this linear relationship, which again, we would expect in a pure ideal system, because since the IMFs are rather similar, we'd hope that they'd have similar vapor pressures. And in this case, the composition of the vapor matches the composition of the liquid. However, some interesting things start happening as A starts becoming more volatile. In this case, not surprisingly, since A is more volatile, it is more likely to be found in the vapor phase than B. So by the point that when you reach that A being 1,000 times more volatile than B, by the time you get to a mole fraction of even 0.1, you'll find that the vapor is quickly entirely A, because it's going to evaporate so much more rapidly than B, which is going to be at this point rather non-volatile in comparison. And so hopefully this makes a lot of sense of how we can, how the relationships in between volatility is going to help control the composition of the vapor. However, this also has some interesting implications for the total pressure of the system. So as A becomes more volatile, what we find is that in comparison, as I decrease the amount of mole fraction of A in the vapor, what I'm going to find is that the total vapor pressure is going to quickly drop. And this is largely due to the fact that since A is so much more volatile, as I decrease its composition, it has kind of this uneven effect as it becomes more volatile. However, if they're equally volatile, what we find is that, well, as I decrease A in the vapor, well, B is just as volatile as A, so they don't actually change the total vapor pressure. But again, this is hopefully a useful way of looking at the sort of controls that the volatility of A and B can have on the real composition of the system. And we'll be exploring kind of the controls that these vapor pressures can have on real systems as we continue through the next several lectures, as they'll greatly control the dynamics of the liquid vapor equilibrium and can have some important functionalities in terms of separation schemes. However, one of the other important controls that we have on the pressure is actually going to be temperature. And we've seen this any number of times because as we illustrated for the pure phases, generally as temperature goes up, so does the volatility. And that's not just of the mixture, it's also of the pure components. And so we're going to see this track as we look at the effects of the vapor pressure of both the components of the mixture and of the total system, that there will be a certain temperature dependence. And what we'll find is that we can use our expressions of the temperature dependence of a pure component, which we illustrated in last chapter, where the um, vapor pressure at a temperature 2 can be related to the vapor pressure at our reference condition, often 298 degrees Kelvin, and using the enthalpy of vaporization and the differences in temperature, what we are going to generally find is as the temperature goes up, so will the vapor pressure. But this is going to hold for both component A and for component B. And so we can go ahead and substitute in these two expressions. And what we find is just like we can use the enthalpies of vaporization for a pure component to determine the vapor pressures at elevated temperatures, we can do the same thing for the vapor pressure of a mixed phase, as its pressure and thus its composition will likely change as an effect of temperature, and this will be largely modulated by the difference in enthalpies of vaporization, just as the vapor pressure at a room temperature is largely modulated by the comparison of the vapor pressures at that temperature. So we'll go ahead and explore what this looks like in a little bit more detail next time. Until then, take care.